In this video, I'm going to show you step by step how you can conduct a chi-square test for independence. Here is the example presented in the textbook. The sample size is 100, so there are 100 kids. They had different preschool backgrounds. The numbers in the row total shows like 47 out of this 100 kids attended public preschool, 18 of them attended private preschool, and 35 didn't go to preschool. Information is also collected on their behavior in kindergarten. So they were rated poor, average, and good. And here is the summary information. So the research question is to investigate whether there is an association between children's attendance in public and private preschool and their behavior in kindergarten classroom. First, you need to be aware that the data presented here is not the original data format we usually see in SPSS. Rather, if you see the dataset in SPSS, you can see, like I did here, you would have 100 lines, each line for one observation, and we'll have at least two variables. I gave an ID number for each of the children. And then I have a school, which means their preschool background, which have a value 1, 2, and 3. And also for each child, in addition to the preschool background, also their behavior rating in kindergarten. With that information in mind, we actually need to know that the chi-square test of independence usually start with a cross-tabulation like we have here. The two variables you are interested in examining, they are put together in this table and showing the frequencies. For example, out of those 47 children who attended public preschool, 12 of them were rated poor in kindergarten, and 25 were rated average, and 10 of them were rated good, so on and so forth. So what we have here in this table, those numbers, they are called the observed frequencies, okay? And in order to calculate the chi-square test for independence, we need to have a table or information that's called expected frequencies. Okay, this is what I'm going to do to make my calculation easier. I'm just going to copy the same table structure so I can create a table for so-called expected frequencies. I'm going to use the same row total and column totals. Okay, so what I do is copy and paste the values for those column totals and copy and paste the values of the row totals. So this is the formula for calculating the expected frequencies. The formula says you use the total frequency of the row times the total frequency of the column divided by the total sample size, which means for kids who attended public preschool and who were rated poorly in kindergarten, for this particular cell, the expected frequency equals the total of the columns times the total of this row divided by the total sample size. Okay. I can copy and paste what I did here to other places, but just make sure when you move across lines, you always use the number from line 14. So I'm going to fix the line to 14 when I copy and paste this formula. Same deal, when you try to copy and paste across columns, you always make sure it's across the column, but you always use the number from column F in your calculation. So this is what I'm going to do. I'm going to fix the column F as well. Okay, so this allows me to simply do a copy and paste for the other cells. All right, if you want to make sure you did the right thing, what you can do is just double click on one cell, make sure it did the product of the row total times the column total is in, and divide by the total sample size. I think we're fine at this point. And this one is the formula you use to calculate the chi-square statistic. It's actually pretty straightforward. You just use the observed frequency of the cell, find out the distance from its expected frequency, square the difference, then divide by the expected frequency. You do this for every cell in your table and add them together. Okay, I actually have another step to simplify my calculation. I just copy the table structure again. And this time, I'm just going to simply find out for each cell what's the difference between the observed and the expected frequencies. Since I have to take a square, so I'm going to time again the observed and expected frequency difference and divide by the expected frequency of that cell. Okay, I'm going to again repeat this same process for the other cells. You can just do a simply copy and paste. That's the individual divisions for each of the 9 cells. Okay, then the chi-square value we're looking for is just the value, the sum of the 9 values in the table. Okay, so we have a chi-square observed that is 11.50. Next, we're going to look up the chi-square critical in table B2. So we need to know what's the alpha value. We're going to use alpha equals 0.05. And what is the degree of freedom? The degree of freedom actually equals to the number of rows. You have 3 rows less 1, so 3 less 1, and times the number of columns less 1. How many columns we have? We happen to have 3 columns. Well, poor average good, and 3 times less 1 there. So we have, if you do the calculation, we have a degree of freedom that's 4. Okay. All right. So with alpha equals 0.05, the degree of freedom of 4, you have a critical value that 9.49 from the table, 9.49. So you have a observed chi-square value 11.50, which is greater than the critical chi-square value 9.49, and the decision is to reject the null hypothesis and conclude, you're going to conclude that there is a significant association between children's preschool background and their behaviors in kindergarten. So statistical significance is one side of the coin. The other side of the coin is the measure of practical importance, and most likely we're going to call that effect size, measure effect size. In the chi-square test for independence, we used Cramer's V statistic to measure effect size. And here is the formula for calculating Cramer's V. Chi-square is the calculated chi-square statistic. N is the total sample size. L is the smaller value of either the number of rows or the number of columns. In our case, we have 3 rows and 3 columns, so L equals 3. Then we put down for Cramer's V that equals square root, and under the square root we have the chi-square divided by 100 times L subtract 1. Finish our calculation. We have a Cramer's V that's 0.24. Since 0.3 is considered as medium effect size, the 0.24 we got here is considered like weak to medium effect size.